I'll begin. Dear Father, we thank you for this day. Thank you for a week almost completed. Pray that you just bless this class. Help us to glorify you again, Lord, in what we do. In your name I pray, Lord Jesus. Amen. All right, so picking back up at the tail end of lecture 2 here, I should define for you. I'm going to pick up here at the cyclic subgroup. We'll let G be a group. And then if it's multiplicative, we do one thing. If it's additive, we do a different thing. All right. Otherwise, I don't really have a notation. But if it's multiplicative, and we're going to let, let's say, X be an element of the group. I guess we usually use A here. A an element of G. All right. Then this notation, angle bracket A, what that means is E, A squared, A cubed, dot, 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 and so forth and so on forever and ever. All right? And on the other hand, if we use an additive group, the so-called cyclic subgroup generated by A is equal to 0, A, 2A, 3A, which of course, I mean, let me write 2A a little bit differently. 2A is what? It's A plus A. You get the idea anyway. 3A, 4A, and so forth and so on. So these are the so-called cyclic subgroups generated by A in the multiplicative sense and also the additive sense. All right. Now, so then what? I've been calling this thing a cyclic subgroup, right? So we should probably actually prove that that's the case. So here's a theorem. The cyclic subgroup generated by A is in fact a subgroup of G, with that defined as above. Okay, so the proof, how's it go? Let's see here. I'm going to use multiplicative notation. If that's all right with you guys. Well, I suppose even if it isn't, I'm still going to do it. Okay, so what is this? First of all, E is an element of the cyclic subgroup generated by by A. By what? By definition, right? So therefore, this is not equal to the empty set. All right. Also, it's clear what? It's also clear that the cyclic subgroup generated by A is a subset of G, right? Because how do we form the cyclic subgroup? We form it by looking at the identity, A, powers of A. All of those things are necessarily in the group by the axioms of the group, closure axioms, right? Okay, so then let's let A to the J and A to the K be elements of the cyclic subgroup generated by A for some J and K in, let's say, the natural numbers, right? I don't think, I mean, it's clear that if we multiply the identity times anything, it's back in the group again, right? So let's just look at these again. I guess if you want, fine, let me just be complete. I might as well just do this, right? There. Now those are two arbitrary group elements, right? So let's multiply them. A to the J times A to the K is equal to what? A to the J plus K, right? Now I suppose I haven't proved that for you in here, but we could prove that by induction, all right? But the thing is, what does that mean then? J plus K is an integer. I mean, excuse me, it's a natural number, or 0, right? It could be that both J and K is 0. This could be the identity times the identity, for instance. And so thus, what? A to the J times A to the K is again an element of the cyclic subgroup generated by A. So apparently the cyclic subgroup generated by A is closed under multiplication. So what does it remain to do? What else do we need to show? I'm using the what? I'm using the two-step subgroup test, right? So the thing I need to check still is closure under inverse, right? So, oh, I think I'm wrong. I'm sorry, guys. I did this. I think I did this. Just a second. I stepped too far away from my notes and got into trouble. Oh yeah, I'm an idiot. What's the definition? I've stated the definition wrong. So sorry. This would work for some examples, but it's just utterly wrong for others. It's funny, it didn't get me into trouble yet. So the definition actually is this. It's a to the n, such that n is an element of the integers. And here it's na, such that n is an element of the integers. So basically we just build in negative powers as well, right? So in this proof, I shouldn't do n union 0, I should do integers, right? But good news, the sum of integers is again a what? An integer, so no harm is done. This becomes more mission critical in the next part of the argument, right? Let aj be an element of the cyclic subgroup generated by A for some j in the integers, right? Note what? Minus j is an element of the integers. Thus, excuse me, a to the minus j, right, which by the way is equal to a to the j inverse in the group, is an element of the cyclic subgroup generated by A. Because it's, again, an integer power of A. So it's in the cyclic subgroup generated by A. And there you have it. Thus, by two-step subgroup test, we have shown that the cyclic subgroup generated by A is a subgroup of G. All right. This is, of course, a pretty important subgroup, right? I mean, of the ones I've studied so far, this is probably the most important example I've showed you. In fact, we'll spend a number of days talking about cyclic groups in here. All right. Galen has a slicker argument than mine. He uses the one-step test at the top of page 63 for what it's worth. All right. I'll show you an example of this, all right? Let's pick at U10, right? What's U10 equal to? Let me do U100. Oh, no. Tell you what, let's do Z14 there. 0, 1, 13, right? If we look at the cyclic subgroup generated by 2, what do we get? 0, 2, 4, 6, 8, 10, 12, and then you're back where you started. And I shouldn't use those brackets. This is an error in my brain we need to rewire. This should be what? Yes. The angle brackets mean what? Cyclic subgroup generated by element, yes. Okay, these are different. How about the cyclic subgroup generated by 3? I think you see where this is going. Oh, wait a minute. Then where do we go? Go ahead, we go to 1, 4, I can't do math, 7, 10, 13. Then where do we go? 2, 5, 8, 11, Oh, and now we're back. And now we're back. That's wacky, isn't it? And so this, by the way, is the same as a cyclic subgroup generated by 1, right? If you just do 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. That's, what's that? Nope, these are sets. Multi-sets are dead to us. This is not linear, so we use sets. I mean, you can reorder the elements. We don't assume an ordering. But the point is, they're different generators, right? So this 1 and 3 apparently are both generators for Z14. What if we look at 4? 0, 4, 8, 12. What do we get next? 16, which is 2. I'll write 2 down here. Then what? 6, 10. Oh, and then we're back, right? Some interesting data to notice while we're here. Let's smell the roses. What's the order of 2? The subgroup generating by 2. 7. The order of the cyclic subgroup generated by 3 here is 14. The order of the cyclic subgroup generated by 4 is what? 7. Interesting. Right. What's the difference between 3 and 2 and 4 as it relates to 14?
One shares a factor and one doesn't.
Right. So we say that 3 is relatively prime to 14, right? Anyway, we have more to say about this some other day, but these are interesting patterns to notice. Okay, so another important subgroup, I mean, we're going to work a lot more with these cyclic subgroups generated by an element. I'm just throwing it out there so we have it in the hopper. Our next definition, so-called center of a group, ZG. What is this? This is defined to be G in G such that Gx is equal to Xg for all x in G. So it's the set of elements in the group that commute with everything in the group. All right? You can prove that this is a subgroup, right? It's probably good for me to go through that with you guys. So let's do that. First of all, notice that G times E, E times X is equal to X times E for all X in G, right? So what's that show? E is an element of what? Of the center. That shows that the center is non-empty. All right. Next, suppose that G and H, I'm going to use A and B actually. Suppose A and B are elements of the center. So what's that tell us? That tells us, for instance, it tells us that Bx is equal to Xb for all x in G, right? Hence, if you multiply that on the right and the left by B inverse, what does that give you? Yeah, by the right and the left of B inverse, what does that give us? So multiply this data we have right here on both sides by B inverse. Of course, I'm using associativity here, right? Technically, I'm using an amped up version of associativity. We could spend several days proving carefully. You'll forgive me if I don't require you to learn that just yet or ever. And this implies what? See what happens? These are the identity, right? This is the identity. And so this simplifies to what? X B inverse is equal to B inverse X for all X in G. So, with that in mind, consider if we look at A B inverse times X, what happens? We can do what? We can use associativity to regroup like that, right? I can flip B inverse and B because of what I just proved in purple, right? But then, what can I do? I can flip A and X. I can flip XA to AX to XA because, right? So this is because A is an element of the center, right? And what does that show? This identity, right, is true of what? For all X in G. So therefore what? What have I shown? Let me add some parentheses here to emphasize what's going on. We've just shown that A times B inverse commutes with everything in the group on the basis of the assumption that A and B are in the center. This shows that A B inverse is in the center. Thus, by one step, subgroup test, the center of the group is a subgroup of G. All right. I told you guys that the centralizer, I said you could look at an exercise in the book. Would you like to see me prove the centralizer is a subgroup as well while we're at it? I'll probably regret this as I consider what I didn't cover today. But if you guys want me to, I'll do it. So what's the centralizer? The centralizer of A, by definition, is the set of X and G such that AX equals to XA. All right? So just the set of elements which commutes with a particular fixed element in the group. All right? So there's a theorem, of course, for each A in the group. The centralizer of A is, you guessed it, a subgroup of G. These things are interesting in later applications. That's why we're introducing them. It's not just, because we get giddy at the application of 1- and 2-step subgroup test, although that may be true. Maybe more so for me. Anyway, so let proof. What are we going to do? Let us note, first of all, EA, AE is equal to EA, thus E is an element of the centralizer of A, right? So the centralizer of A is not empty. Suppose A and B, oh, bad choice of variables, A. Yes, sir?
What's the centralizer? What is that?
It's defined right here. So suppose X and Y are an element of the centralizer of A. Again, it's the set of all elements which commute with A. In contrast, the center of the group is the set of all elements in the group that commute with everything else in the group. Similar, but different. Anyway, so if X and Y are in the centralizer, then what? We have that AX is equal to XA, and we also have that AY is equal to YA, right? So it's almost the same argument we just went through here. I'll do it two-steppy this time. First of all, Thus, A inverse AX A inverse equals X A inverse X A inverse, which implies that canceling the inverses, X A inverse equals to A inverse X. So therefore, oh, I'm an idiot. That's not what I wanted to do at all, is it? I'm not trying to show A inverses in the centralizer, am I? I mean, it is, but that's not the point. I'm trying to show that X inverse is in the centralizer, right? So to do that, I should multiply before and after by X inverse. X inverse AX, X inverse equals to X inverse XA, X inverse, which of course implies that X inverse A is equal to AX inverse, and that's what I need to show that X inverse is in fact an element of the centralizer of A, thus showing that the centralizer is closed under inversion. It remains to do what? If we're going to use a two-step test, I also need to show it's closed under multiplication. So what do I need to show there? I should check out A times xy, right? I start with that. What's my goal to show? My goal is to show that's equal to xy times A. Showing that can be manipulated to xy times A is what it takes to show that xy is in the center of A, centralizer of A. So, you just apply the data. This is going to give me xa, y, using the fact that x is in the center, right? And this is going to give us x times ya as y is in the center, right? Thus, that's what we want, right? A times xy is equal to xy times a. Therefore, xy is an element of the center of A. Hence, by two-step subgroup test, the centralizer of A is a subgroup of G. Here. I actually have that typed in the notes now. I took the liberty of editing the last page. Sorry for doing that. I'm trying not to edit the ones before, once we were to the next, but it was too egregious. I had to fix it. All right. That brings us to lecture 3. Lecture 3, if I can find it, is on symmetry groups and ultimately the dihedral group. All right. If I can find my lecture 3, this is lecture, oh man, I got lecture 1, I got lecture 2. Where is my lecture 3? Huh. Oh, it's hidden here. Any questions about anything before I go on here? I'm actually going to use the projector a fair amount for the lecture 3 material, but I want to start by just talking about something with writing because it's important. The reason I'm going to use the projector for a bit is so that we actually have at least 10-15 minutes. Wait a minute, do I have 10-15 minutes? So we have 10-15 minutes to draw pictures. Yeah. I guess I better get on with it, huh? So, what is a symmetry? Where does the discussion of symmetries fit into all of this? Yeah, I think all of that sort of falls under the umbrella of a much larger topic, which I'll introduce for you guys now, and that's the problem of permutations. So you've already studied permutations. I don't know if you've thought about them this way or not, but here's the definition. And I'm giving it for a non-empty set to avoid pathologies I'm not aware of. But if the set is non-empty, then if you have phi, a mapping from S to S, right, a bijection. You guys know what bijections are, right? It's one-to-one and onto. It's a surjection and injection. if you have a bijection from a set to itself, then phi is a permutation. So this actually allows us to invent an interesting group. In fact, this is really more in tune with what Galois did to start with, to study permutations of roots. But here's the deal. Well, a theorem, really. If G is the set of permutations on S, not empty, okay? Then G forms a group with respect to what? Yeah. Where did I just set these notes? Is this the one? Sorry, guys. Oh, I'll do that. Is the... Oh, yeah. Not empty. That's what I said, but not what I wrote. Thank you. Of course. So it's with respect to function composition, all right? So what's the proof? I will start you out. How about the identity map on S? How do you define the identity map on a set? I'll drop the S. Id of x equals to x for all x in S. Right? This is a bijection, right? A permutation. Right? Thus what? Well, thus G is not equal to, right, the empty set, for one thing. I guess that's not really my point, though. Let me shut up. So I'm arguing that the identity map serves as as the multiplicative identity. So if F is a mapping on S, right, if it's a bijection, then notice if we look at F composed with the identity, right, acting on X, what do we get? Definition of function composition, right? So what does this show? F composed with the identity is equal to F, right? And you can show that the identity composed with F is also equal to F through a very similar argument, right? Therefore what? The identity is equal to E for this group. Right, define G to be a set of permutations. So there's the proof that the identity map is in fact the identity of the group with respect to composition. Now I'm going to leave it to you guys to prove to me that this is in fact a group, that it's closed under composition and inversion. That's not that hard to do because you're given that this is a set of bijections. So use that. All right? So that's one of your homework problems. Okay, so the rest of this lecture, though, is really about looking at a particular kind of bijection that satisfies a little bit more structure. So I'm going to use the projector here so I get to where we need to go in time. Because also a lot of the details I'm about to go over are not, well, I mean, I'm not saying they're not important. I'm just saying that they're things you should read. They're a little bit, these are much more in tune with the central focus of this course at the moment. what I'm about to project, I want you to know I think you should be able to do, but I don't mind not focusing on it. Where did I put my laser? My laser. Oh, thank you. It's a good thing I have you guys. Oh, funny thing, yeah, turn the computer on. Let's see here. It's misbehaving again. I said off. Is it showing up? Yay. All right. So as I just mentioned to you, a permutation is a bijection, and the set of all permutations forms a group. That's for an arbitrary set, right? That's like a really big example. All right, but anyway, if we look at Rn, the bijections on Rn that are especially interesting are the ones which preserve distance. All right, these bijections are called isometries. So just a little bit about distance, right? In Rn, we have vector length, sum of the square root of the squares, right? This is a norm in the sense it's got triangle inequality, absolute homogeneity, it's positive definite. You can define the distance between points as we did in Calculus 3 or in my linear algebra or in Dr. Scambordis' linear algebra. I know he did it in there. You can't deny it. He spent the first 2 weeks of class doing like Cauchy-Schwarz inequality and stuff because he loves it, didn't he? He did it, didn't he? Don't deny it. I know he did it. I heard him talking about it. You all know this. Or you've seen it. Anyway. So we have a distance function, and we can define it in terms of the dot product, right? Isometry means same measure. Yay. And so in particular, oh, shnikes. I wanted to make this n and n. I'll fix that as soon as I get around to it, because everything else I say here works for Rn. Galilean is primarily interested in R2, but I think it's important to mention that these things hold for Rn as much as we can without too much work. So an isometry is something that maintains the distance between 2 points, all right? This is what an isometry is. So a fundamental theorem of isometries is that the isometry preserves dot products if and only if the isometry fixes the origin. So if the origin sends 0 to 0, if the isometry sends 0 to 0, it's going to preserve dot products. And this ultimately allows us to, and the proof is actually pretty easy to follow. Here it is. It's just like a little dot product identity thing. If I had more time, I'd go. If you want to, I'll go through it carefully with you in office hours if you ask me. So that's first thing. Isometry which fixes the origin preserves dot products. I then would remind you that dot products define angles because of the Cauchy-Schwarz inequality. Because we know that the magnitude of the dot product is less than or equal to the product of magnitudes of the vectors involved, provided the vectors are non-zero, we can form this quotient. This quotient has magnitude less than 1. It follows that this is represented by a cosine between 0 and pi. Consequently, we can define angle in n dimensions by this ratio. And we have this theorem. If you have an isometry and theta is the angle between vectors v and w, then theta is also the angle between the image of the vectors under an isometry, phi of v and phi of w. In other words, isometries preserve angles between vectors. We started out by assuming that it preserves distance between points, and for free, we get preservation of angles between vectors. It's pretty cool. It's so much more than that, though. I mean, the proof is actually, like, not too bad, right? You just use what we just had before, which was that the isometry preserves dot products if it fixes the origin, right? I do need that. I think I'm supposed to have that it's a origin fixing isometry here. There's something missing. Oopsie. Oh well, don't tell anybody. Yeah, otherwise I don't get this, right? I need that phi of v dot phi of w is v dot w. That's true if like phi of 0 is 0. That was required in this proof up here. So, all right. Moving along. You can define the set of isometries on Rn to be isom Rn, And you can just denote the set of origin fixing isometries. In other words, phi of 0 is 0 for all those by orth. These are the orthogonal transformations. Those are actually a subgroup of the isometry group. Sounds like a homework. It is your homework, yes. That's actually not that hard, all right? You just have to think through it. Here's how you define a line. Here's how you define a line segment. I don't really use these per se. I thought I needed to, but not really. So there are really three kinds of isometries. There's rotations, there's reflections, there's translations. And they're just what they sound like. A rotation fixes the origin and rotates the vector through some angle, right? Reflection flips points across some line, right? Or if the point is on the line, it just fixes it. And translation is one of these dudes, right? It just shifts everything by a vector. There's also glide reflections. If you want to, you can read chapter 28 of Galilean about that. Don't do it now. It's full of group theory you don't know yet. You got to put that off. Anyway, so after about a page or two of pretty subtle and beautiful arguments, you can prove the following theorem. Every isometry of Rn is a bijection. More than that, every isometry which fixes 0 is a non-singular linear transformation. I said nothing about linear transformations in the definition of isometry. This is something that comes from much effort, okay, which we will not make, relax. I thought about putting that in this course, but then I thought, I should make this course friendly, and I removed it, okay? But I want to tell you about it because it's important to know about. Once you know that, though, there's lots of easy theorems we can prove, which is why we're covering this, because they're good theorems that test the subgroup test and all the things that we're learning right now. This theorem, for example, that the isometries form a group with respect to function composition, all right? The key there that makes this easy is that you know that they're non-singular linear transformations from up here. I don't quite know that, do I? I know that they're bijections at least, though, right? I know that the orthogonal group is non-singular linear transformations. So be careful. But with this data up here, this is an easy theorem to prove. Okay? And by the way, once you prove this other one, you can just use the subgroup test because it's, after all, a subgroup of the set of all permutations on Rn. Right? You don't have to reinvent the wheel. You can use a subgroup test because it's a subgroup of the set of all permutations, which you've already proved as a group in the earlier homework problem. In the particular, you prove it for an arbitrary S, but in particular it applies when S is equal to Rn. Sorry, I keep talking about your homework. It's bad form. Let's see here. That's your job, right? Definition, I'm just kidding. So this allows us to define what are called orthogonal matrices. And that's the set of all standard matrices of orthogonal transformations. That's denoted ONR. And basically that's just like standard matrix of T, where T is an orthogonal. This makes sense, right? Because we just got done saying that the orthogonal transformations are non-singular linear transformations. So the standard matrix is defined. You know it, you love it, you can calculate it. And you can also show, in fact, this is a homework problem, that the orthogonal group of order n has this form. You can derive that from the earlier data here. I may have assigned you this before in linear, but not quite with this language, yeah? So, getting to the point here. Symmetry groups, so, I mean, sorry, I had a little jibber jabber here I'd like to read. So we turn our focus to n equals 2. The isometries of the plane are particularly nice to visualize and study. You can envision what happens to shapes as they're transported by an isometry. Circle maps to circle, line maps to line, angles between lines are preserved, right? So if you think about what that does to shapes, how do you make a shape? You take lines, you put them together by certain angles that are fixed, right? So if you feed a shape to an isometry, what does it do? It maintains the shape, right? That's why isometries are sometimes called rigid motions. And so they maintain the shape of rigid shapes. And so if we focus our attention then on n equals 2, that is where Galilean lives and where we're mostly living. And that's where I'm going to talk for the remainder of today about. We can fix a particular subset of R2. Mostly I'm thinking about a triangle or a square or a pentagon or some regular polygon. But it could be other things, like it could be a car or, a two-dimensional car. I don't know, you pick your favorite two-dimensional shape. You can ask what's the symmetry group of it. In other words, what isometry of the plane leave that object unchanged as they map it, right? So, excuse me, stupid example. If you take omega equal to R2, the isometry group of the whole plane is just all isometries. Not a very good example, sorry. But that brings us to the definition of the dihedral group. That Dn denote the symmetry group of a regular unit side length n polygon. We call this the dihedral group of order 2n. At this point, I'm going to put this away because that's the context that dihedral groups live in. They're particular subsets of the set of all distance-preserving maps on the plane. All right? They're in particular the distance-preserving maps that leave regular polygons fixed. All right? So let's look at what that looks like explicitly. Oh, why did I do that? So let's start with the simplest example. Let's start with the symmetry groups of an equilateral triangle, right? This symmetry group is known as D3, or AKA the dihedral group of order 6. So some other books will call this D2n. Beware of that. Well, D6, quote unquote. I'll put some quotes on it because that's not what we call it. But if you just start reading stuff on the internet, it might be called D6, all right? So here's the idea. Here's a triangle, hopefully equilateral. I should have brought some demos or something here, right? What can you do to this triangle in terms of, now I told you, I spilled the beans, isometries are either rotations or reflections or translations, right? Translations are out. If I translate the triangle, it's no longer where it was again. So throw those out, all right? But rotations, those will work, right? So to keep track of what we're doing, we usually number them 1, 2, 3, or whatever, right? So if I do a rotation clockwise, right? Say clockwise rotation, what does that do? It puts the 3 up here, it puts the 1 down here, it puts the 2 over here. Rotation by 60 degrees. And what happens if I do a rotation, same rotation to this again? Right? Let me make sure I did it right. Yeah. You can't trust me. All right, so I'm trying to do counterclockwise rotations. I have a vice. Counterclockwise. Okay. Yeah. I know the 3 is right. That's about all I'm sure about. 3. So the 2 gets pushed over here, and the 1 gets pushed up there. I'm doing a counterclockwise rotation by 60 degrees. Of course, what happens if you go back here? If you rotate one more time, right? So geometrically, it's clear that this rotation is an element of order 3, right? You rotate by 60 degrees 3 times, back where you started. Is that right? Yeah, 120 degrees. I'm an idiot. Sorry. Yeah, let's say that this is our 120 degrees. That would be entirely more reasonable. Thank you. I think my notes currently say 60 degrees somewhere. Strike that from the record. Obviously 120 degrees. Now that's not all there is though, right? What else can you do? You can flip it like that, right? So a reflection, we could call this, say, F2. The reflection about the second axis So that would be 2 fixed, and then the 1 and the 3 flip. That's also distance preserving. That's an example. It's an isometry which leaves. Golly. Yeah, maybe I've used the projector for the wrong part of the talk. I don't know. Let's see here. Sorry, I don't have such pictures in the notes. Okay, so so then what happens? You can also do what? Yeah, you can rotate the reflection. You could do, say that this is like, basically, I guess I should really put F2 up here and F1 down here. It's probably better labeling. But anyway. So this one would be what? So 1 is fixed, right? And that 3 and 2 get swapped. That's F1. And like you said, you could rotate this, right? And what would that give you? One, 2, 3, right? You could rotate this the other way. That would give you what? Go clockwise instead of counterclockwise. So 1, 3, 2. You get the idea, right? Now, there's something beautiful that's true about these dihedral groups. There's a simple, yes, you can do these kind of pictures. This gets much worse when you're looking at like RD6, right? Or D7, looking at a septagon, or what is it? It's not a Decepticon. It's or the D8, the octagon. It sounds more interesting. But there's something beautiful that happens. There's this simple relation, and here it is. It's FRF equals to R inverse. This is a relation that is going to be true between the fundamental rotation and the reflection. Let me show you why that's true. So to prove this little relation, there's really 2 cases to consider, but I'll just kind of like focus in here on a little. So suppose that you have, an n-gon, and suppose this is like the first one, the second one, and the third one, right? And we're looking at this being, F. And the rotation is the counterclockwise one, right? So let's do FRF. First of all, F does what? This keeps going, 3, 4, and on the other side over here, if my picture was bigger, it would have n minus 1, right? Or n, I'm sorry, n, right? How many are there? N, yeah. Duh. This is over here is 4. I just only want to draw the 3 to keep the picture not so busy, all right? So if I do a flip, this is 2, 3, 1, right? If I rotate, what do I get to? We're rotating counterclockwise, right? So 1 goes to the top, 2 goes over here, and what's over here now? Yeah, n. Then what happens if we flip again? We get 1 upstairs, and we get n over here, we get 2 over here, right? Now, on the other hand, what if you go to the start and you just do R inverse? What do you get? Clockwise rotate, right? 1 goes to the top, 2 goes over here, n goes over here. Check it out. This and that are the same. You can do a similar argument. Like the picture looks a little bit different when n is even. For n odd, there's always a reflection like this. But the point is, you get this awesome relation. The reason I say that's awesome is it allows you to calculate in a dihedral group without drawing these pictures. All right? For example, and I'll stop here with this, but this is really the main thing. By the way, this is not about D3 or D4 or D5. This is about Dn, what I'm saying here. Yeah.
Is a rotation, like a normal rotation, always going to be counterclockwise?
I think so, but I think, I mean, my default is to make it counterclockwise, but you could present the group either with a clockwise or a counterclockwise. Like, I don't think it would change that relation at all. The other thing, of course, is, I mean, a couple fundamental things. Of course, f squared is equal to the identity. I mean, I didn't say that yet, but that's kind of an obvious, like, low-hanging fruit, right? If you reflect and then reflect back, you're back where you started. And so let's look at a calculation. For example, if I look at f r squared times f r inverse, right? And let's look at this. It's like f times this, right? What's that equal to? That's f r sorry, I just going to put an r here. Keep it simple here. So f r. So we can do what? We can simplify this like this, right? And what's that give you? Now, I didn't say our context here. Let's suppose we're in D3, okay? Right? Then what would that say? In D3, r cubed is equal to e, right? Thus, if I do r to the minus 2, I get what? R. So this is really equal to r again. So the product of f and rf r inverse is that. What happens if we reverse the order here? Rf r inverse times f, what do we get? We can change the r inverse to what? R squared, right? Using the fact that it has order 3. And then what does this give you? But this is what? This is our inverse by the thing we derived geometrically over here. At least I gave you a partial explanation for it. Our inverse RF, which is F. Check it out, folks. What we've just shown in D3, right? Yeah?
You said by the thing we put over there, isn't that f r f?
What do I have? Oh, man. Schnikes. Jess, thank you. It hurts right now, but thank you. So that's R, F, I mean FF is E, right? F, R, F, F, R, F. Roof, roof. No. Roof, roof. I don't know. What were we looking for? Now you guys got me distracted here. FRF is our inverse, right? So this is RF. Okay. So this and this are not equal. In fact, you can show, I don't recommend you try to show this, but E, R, R squared, F, RF, R squared F. This is a nice presentation of D3. And that's why it has order 6. These are unique elements of D3. And that, by the way, shows that D3 is a non-abelian group. How much matrix multiplication do we have to do to show the non-abelianness here? None! That's what makes this awesome, is now we have a non-abelian group where we don't have to multiply matrices. And once you master this little trick right here, you can manipulate these all day long without drawing a picture, which is fantastic. Anyway, I'll try to do another example of these some other day. Thanks, guys, for your patience. Have an excellent weekend. Thank you for your homework.